So in today's lecture, we will continue with some example based on monotone convergence theorem. Okay, we know a monotone convergence theorem implies that if sequence is bounded and monotonic, then sequence is convergent. Okay, so the next example is we have to show the sequence whose n term is convergent. Okay, and we have to use here monotone convergence theorem. That is, we will show sequence is monotonic, either increasing or decreasing, and it is bounded. Okay, so we will first prove the sequence is monotone. Okay, so we will find the n plus 1 term of the sequence. Okay, so yes, n plus 1. This is the n term of the sequence. So from this we can derive n plus 1 term. So n plus 1 term of the sequence will be replace n by n plus 1. So first term will be n plus 1. Instead of n, we have write n plus 1. So 1 upon n plus 1 plus 1. So n plus 2. Then next term will be n plus 1 plus 2. So n plus 1 plus 2 means 1 upon n plus 3. Up to here 1 upon n. So here n plus 1 plus n plus 1 minus 1. Okay, so instead of n, here n plus 1, here is n plus 1, and here is minus 1. So n plus n twice n. 1 plus 1 minus 1. So 1 minus 1 remains, and only 1 remains. So twice n plus 1. So 1 upon twice n plus 1. At last 1 upon n plus 1. So in this term here it will be n plus 1 plus n plus 1. So 1 upon 2n plus 2. So twice n plus 2. So this will be the n plus 1 term. What we have done? Just replace n by n plus 1 in each term. Okay. So now we will take difference between Sn and Sn plus 1. So Sn plus 1 minus Sn. Now see, here second term is n plus 2, here third term, here first term is n plus 2, here third term will be n plus 3, here second term will be n plus 3. So all the term 1 upon n plus 1. Okay. So here at some time, so first only first term is different, and here last two term are different. Okay, so whenever we take subtraction, this middle part which is same as here. Okay, so from here n plus 2, okay, to the term before this is 1 upon n plus n. Okay, that is 1 upon twice n, and later on twice n plus 1. So here term like 1 upon n plus n. So this part 1 upon n plus 2 to 1 upon n plus 1. So here also 1 upon n plus 2 to 1 upon, before this term 1 upon n plus n. So this part up to 1 upon n plus 1 is here also. Okay, so 1 upon n plus 2 to 1 upon n plus n. 1 upon n plus 2. So here 1 upon n plus n. Okay, this part is same. So whenever we will take difference, this part will then cancel. So taking difference, so here we are written first here n plus 1. So here only these two terms are different. So we will write this. So 1 upon twice n plus 1 plus 1 upon twice n plus 2 minus of Sn. So what remaining Sn? This all we can, so only one term is remaining, 1 upon n plus 1. So minus 1 upon n plus 1. Okay. Now this is 1 upon twice n plus 2. From this we can take 2 outside, 2 as a common. So here if we take 2 outside, this will remain as n, this will be as 1. So we write this as 2 into n plus 1. Okay, that is twice n plus 2. Now see, 1 upon 2, half of n plus 1 minus 1 upon n plus 1. So half of 1 upon n plus 1 minus 1 upon n plus 1. So half minus 1 is always half. So 1 by 2 of n plus 1 minus 1 upon n plus 1 will be minus of. Okay, so half minus 1 is minus of half. So this implies 1 upon twice n plus 1. Or we can write by taking 1 upon n plus 1 common. So 1 upon n, if we take 1 upon n plus 1 common, this will be like 1 upon n plus 1. Here is 1 by 2. Here is, even if we take 1 upon n plus 1 common, so remain only 1 here. So minus 1. 1 by 2 minus 1, minus of 1 by 2 into 1 upon n plus 1. So minus of half of n plus 1. Okay, that is, this is equal to 1 upon twice n plus 1 minus 1 upon twice n plus 2. Now see, here denominator is twice n plus 1, here denominator is twice n plus 2. Here denominator is this denominator is less than this denominator, means and numerator are same. So this means this number is greater than this number. So the difference must be positive. Okay. So we are subtracting a lower value from higher value. This difference must be greater than 0. So this difference Sn plus 1 minus Sn is greater than 0. This means Sn plus 1 is greater than Sn for all here. And this means sequence is monotonic increasing. This implies sequence Sn is monotonic increasing. So we are done half part. We are just shown the sequence is monotonic increasing. Now, if we show sequence is bounded, then our proof will be over, because a sequence which is monotone and bounded is convergent by monotone convergence theorem. Okay. Now our sequence, see what are the element of the sequence? 1 upon n plus 1, 1 upon n plus 2, 1 upon n plus n minus 1 up to 1 upon plus 1 upon n plus n. Now, if we observe that 1 upon n plus 1 is always less than 1 by n, because here denominator is n, denominator is n plus 1, numerator is same. So the denominator is higher than this denominator, this number is lower than this number. Similarly, 1 upon n plus 2 is also less than 1 by n, because denominator is greater than this denominator. As denominator is higher, this number is less than this number. So continuing in this way, we can easily observe that up to last term, all the terms are less than 1 by n. Here denominator is 1 upon n plus n. Here denominator is only n. Here n plus n. Here n. So here denominator is greater than this denominator. So this number is less than this number. Okay. So by observation we can say that this each element of this sum is less than 1 by n. So we can write sequence Sn is equal to 1 upon n plus 1, 1 upon n plus 2, up to 1 upon n plus n. But this less than, this number is less than 1 by n, this number is less than 1 by n. Also, every term is less than 1 by n. So this total sum is less than this sum. Okay. But this sum is you have taken n times. These are the n elements. So this sum you have taken n times. So this will become. So this term, sum and this term is same 1 by n. So n times 1 by n, because we are summing 1 by n times. This is nothing but n times 1 by n, which is nothing but n get cancelled. So it is equal to 1. This implies sequence Sn is less than 1. And observe that each term of the sequence, if you take first term, sequence is monotonic increasing, and put n is equal to 1. When we take n is equal to 1, our term will be 1 upon 1 plus 1, so 1 by 2 plus 1 by 3 up to so on, positive term. So first term is positive and sequence is increasing, so second term and third term also positive. So this implies the sequence is bounded below by 0, because each number is non-negative of the sequence. So sequence is greater than 0. Okay. So sequence is bounded. So this implies Sn is bounded. Okay. Since each term of the sequence lies between 0 and 1, the sequence is monotonic increasing and sequence Sn is bounded. So by monotone convergence theorem, this sequence is convergent. Okay. So by monotone convergence theorem. Okay. The theorem says if sequence is monotone and bounded, it is convergent. Okay. So the next similar example is to prove the sequence Sn defined by n term. The n term is 1 upon 3 plus 1, 1 upon 3 square plus 1, so plus up to plus 1 upon 3 raised to power n plus 1. So we have to prove the sequence defined by this n term is convergent. Again we are going to use the same formula or theorem, monotone convergence theorem. We will prove the sequence whose n term is monotonic and bounded. Okay. So we have the sequence n term of the sequence Sn. So we can derive the n plus 1 term of the sequence, which will be 1 upon 3 plus 1 plus 1 upon 3 square plus 1 up to 1 upon 3 raised to power n. Okay, plus 1 and last 3 raised to power n plus 1 plus 1. Okay, how we derive the n plus 1 term of Sn? Just we add one more element to the n term. The term will be last term will be just n plus 1 here. Okay, so 3 raised to power n plus 1 plus 1. First, these n terms are same. First term will be, if we ask find S1 will be just 1 upon 3 plus 1. S2 will be 1 upon 3 plus 1 plus 1 upon 3 square plus 1 up to so on. Sn will be the sum of this n term. So Sn plus 1 will be the sum of this n plus 1 terms. Okay, and the last term is 1 upon 3 raised to power n plus 1 plus 1. Now we will take difference between Sn plus 1 and Sn. Now again see, these n terms are also here. So if we take the difference, this and this will get cancelled, only remaining this. Okay, so in Sn plus 1 remains 1 upon 3 raised to power n plus 1 plus 1 minus nothing is there, so minus 0. So Sn plus 1 minus Sn is this, and this number is positive. You put any rational number, this is greater than 0. So if Sn plus 1 minus Sn is greater than 0, and this happens for all values are here, this applies sequence Sn is monotonic increasing. Okay, now we have to prove the sequence is bounded. Okay, now see here, first term of the sequence 1 upon 3 plus 1. So first element of the Sn in this summation is 1 upon 3 plus 1 is obviously less than 1 by 3, because here what denominator is 3 plus 1, here denominator is 3, so denominator is greater here, so this number is less than this number. Okay, similarly the second term 1 upon 3 square plus 1 is obviously less than 1 upon 3 square, because here denominator is 3 square plus 1, which is greater than 3 square. Numerator are same, so 1 upon 3 square plus 1 is less than 1 upon 3 square. Denominator is greater, the number is lower or smaller. Up to so on, we can say the number 1 upon 3 raised to power 1, 3 raised to power n plus 1 is obviously less than 1 upon 1 upon 3 raised to power n plus 1 is this term is also less than 1 upon 3 raised to power n, because here denominator is 1 upon 3 raised to power n plus 1. The denominator is 3 raised to power n. Denominator is lower than this, so this number is greater than this. Okay, so using these observations, we can say the sequence Sn whose n term is 1 upon 3 plus 1, 1 upon 3 square plus 1 up to 1 upon 3 raised to power n plus 1 is obviously less than. Just replace this number by term higher than their other terms. Okay, so this replace 1 upon 3 plus 1 by the term greater than 1 upon 3 plus 1. 1 by 3 is greater than 1 upon 3 plus 1. So replace these terms by the terms higher than these terms. Okay, this 1 upon 3 plus 1 is less than 1 by 3. This 1 upon 3 square plus 1 is less than 1 upon 3 square. So continuing in this way, this term is less than 1 upon 3 raised to power n. Okay, now this looks like some geometric series, but in geometric series first term will be 1. So we can write this as this equal to, take 1 by 3 as common. So in the bracket here is 1 by 3 into 1, 1 by 3. So here 1 by 3 square and 1 by 3 is taken outside. So here it will be 1 by 3. Next term will be 1 by 3 square up to 1 upon 3 raised to power n minus 1, because 1 by 3 taken outside. So 3 into 3 raised to n minus 1 will be 3 raised to power n. Okay. Now this is the geometric series with common ratio 1 by 3, and we know the formula for sum of these n terms. Okay, so we know the formula of sum of geometric series. Okay, this is 1 by 3 as it is in bracket. Okay, so Sn is less than this is nothing but equal to this, and this is equal to 1 by 3 Okay, we know the formula for geometric series. Okay, so geometric series sum formula is summation of k is equal to 1 to n minus 1, or k is equal to 0 to n minus 1 of x is to power n is equal to x is to power n minus 1 upon x minus 1. Okay, we know the formula. So summation k is equal to 0 to n minus 1. So here series x is equal to 1 by 3. So this becomes, or we can write it also as 1 minus x is to power n upon 1 minus x also. Okay, we can write also that. So this is also equal to 1 minus x is to power n upon 1 minus x. So here we can write this summation is equal to 1 minus 1 by 3 value of x raised to power n. So 1 raised to power n upon 3 raised to power n, but 1 raised to power n is 1. So 1 upon 3 raised to power n upon 1 minus 1 by 3. Okay. Now this 1 by 3 as it is, so this is equal to 1 by 3. Okay, and 1 minus 1 by 3, so 3 into 1, 3 minus 1, so this becomes 2 by 3. Okay, and in numerator there is 1 minus 1 upon 3 raised to power n. Okay, now whenever, so these 3 and these 3 get cancelled. Okay, so this is equal to half of 1 minus 1 upon 3 raised to power n. So Sn is less than this term, because Sn is less than this and this is equal to this. So this implies Sn is less than this term. Okay, and as n tends to infinity, 1 by 3 raised to power n tends to 0. So as n tends to infinity, Sn is less than half. Okay, so as n tends to infinity, Sn is less than half. Okay, because as n tends to infinity, 3 raised to power n tends to infinity, 1 upon 3 raised to power n tends to 0. So 1 minus 0, 1, 1 into 1 by 2, half. So as n tends to infinity, Sn is less than half. Okay, so this applies sequence, and we know each term of the sequence is positive. So each term of the sequence is greater than 0. This implies 0 is less than Sn, and each term of the sequence is less than half. This implies sequence Sn is bounded. So we have proved first sequence is monotonic increasing, and now we have proved sequence is bounded. So by monotone convergence theorem, this sequence is convergent. This implies sequence Sn given in example is convergent. Okay, is convergent. So this is the use of monotone convergence theorem. Okay, now next, a very important point of the sequence is quasi sequences. Okay, so we will first see the definition of quasi sequence, then I will clear the concept what is the quasi sequence. So the sequence Sn is said to be a quasi sequence if for any epsilon greater than 0 we can find natural number m such that distance between the element Sn and Sn, that is mod of Sn minus Sn, is less than epsilon for all m n greater equal m. Okay, now there is very close relationship between quasi sequence and convergent sequence. So first we will see, we will revise what is the convergent sequence. Okay, so definition of convergent sequence was, for if a sequence Sn is said to be convergent if for any epsilon greater than 0 we can find a natural number such that difference between L, in the time L is said to be limit if difference between Sn and L is less than epsilon for all n greater equal m. Okay, so first we will again clear the concept of limit of the sequence. What is definition? A sequence is said to have limit L if for any epsilon greater than 0 we can find natural number such that difference between Sn and the limit goes on decreasing or less than very small number epsilon for all n greater equal to m. We'll clarify the concept using one example. Okay. Now, okay, let our sequence is sequence 1 by m. Okay. So we know the point element of the sequence. Okay. If you put n is equal to 1, so 1 by 1 is 1, 1 by 2, 1 by 3 up to so on. These are the element of this sequence. We will try to plot the element on the graph. Okay. So for n is equal to 1, what is the value of sequence? Whenever n is equal to 1, value of sequence is 1. Okay. So for n is equal to 1, value of sequence say, so suppose here is value 1. Okay. So value of sequence is 1. Okay. This is will be half. So 1 by 3 from 1 to here is 0. So for n is equal to 2, whenever we put n is equal to a1, then if you put n is equal to 2, the value of the sequence will be 1 by 2, this point. Okay. So when we put n is equal to 3, the value of sequence is 1 by 3. Okay. So whenever we put n is equal to 4, the value of sequence will be 1 by 4. Okay. So then our graph will continue as like this. Okay. So this graph is going very close to 0. Now what is the difference of sequence? So our limit is in this case is 0. Okay. So x is equal to n is equal to 0 is our limit. So this is the value of axis, which is y is equal to 0. Okay. So this represents the limit. So the elements of the sequence are tending to 0. So after some point, okay, so we will get a natural number m. Suppose this natural number is say 1, 2, 3. Suppose this is the natural number, say m. Now see, after this m, the difference between element of the sequence, okay, and the 0, Sn and 0 is going very minimized. Okay, very less than some positive number. Okay, they are getting very close after some value of m. Okay, we can say that suppose m is 1000. Okay, so whenever m is equal to 1000, the value of the element, the value of the sequence will be 1 upon 1000, which is equal to 0.001. Okay, so which is very close to 0. So this is the concept of limit of sequence. After some natural number, all the element of sequence are getting very close to that point. Okay, then we say that sequence Sn is converged to the point m or limit m. Okay, see, now when first limit is 1, difference between 1 and 0 is pretty much equal to 1, which is not very small. But as we go after some time, the element of the sequence and the limit is equal to 0 get very close to each other. The difference between them becomes very small. In such a case, we say that the limit of the sequence is equal to the limit. Now, in a similar way, what is Cauchy sequence? Cauchy sequence are the sequence in which again we can find a number, natural number m, such that after that m, if you take the difference between any two elements is very small. Same here. So, okay. So again take the same example 1 by m. After this m, if you take difference between any two elements Sm and Sn, the difference will be very small. Now see, if you take difference between 1 and 1 by 2, S1 is 1, S2 is 1 by 2, difference is 1 by 2. Not very much small, it is small but not so small. Okay, but as we go very after some fixed terms, say m, say after 1000 terms, the difference between any two terms, if you take difference between any two terms, okay, suppose m is 1000, so yes, 1001 term will be 1 upon, suppose m is equal to take 1001. So after this term m is equal to 1000, so yes, 1001 will be 1 upon 1001, and this is equal to 0.001 something, very small. Again you take another value, say yes 2000, so 1 upon 2000 will be again 0.0002 something. The difference between these will become very small. You can see here, first term is 1, second term is 1 by 2, third term is 1 by 3. As we increase the terms, so the elements are tending to 0. Okay, first term is 1, second element is half, third element is 1 by 3. So these elements, so after some time, infinitely many elements are very close to 0. So if you want to take difference between them, see here all the terms are tending to 0. So if you take difference between them, difference will be very much smaller. Such sequence are called Cauchy sequence. Okay, so we will see one very important theorem, which is every convergence sequence of real number is a Cauchy sequence. I already talked about this. I have said that there is very close relationship between convergence sequence and Cauchy sequence. We are seeing graphically. So this means if a sequence is convergent, then it must be a Cauchy sequence. Or we can say, if sequence is not a Cauchy sequence, it cannot be convergent. Okay. So very important theorem, which imply the relationship between convergent sequence and Cauchy sequence. So this theorem, in this theorem, we have to prove that every convergent sequence is Cauchy sequence. Okay. So very simple, very easy proof here. Okay. So let's assume that the sequence Sn is convergent sequence and prove the sequence Sn is Cauchy sequence. Okay. So let sequence Sn is convergent. Okay. Let Sn is a convergent sequence. Okay. So by definition of convergent sequence, for any epsilon greater than 0, there is this natural number m such that, okay, because that we have tried limit, since Sn is convergent, and say Sn tend to L. Okay, so we say that sequence is convergent and L is the limit of sequence. So by definition of limit of sequence, for any epsilon greater than 0, there is this natural number m such that difference between the element of the sequence, say Sn, and limit is less than epsilon for all m greater or equal that natural number m. Similarly, if there is another number here, small m, which is greater or equal to this m, then for that m, this relation is satisfied. That is mod of Sm minus L, also less than epsilon. We write it. Okay. Also, the difference between Sm and L is less than epsilon for all m greater or equal m also. Okay. So each of writing for all m. Okay. So if n is greater or equal m, this is true by definition of limit of sequence. If m is also greater or equal m, this is also true. Okay. So why? Because limit of sequence means difference between the element of sequence and limit is very small after some terms. So whenever n or m is greater or equal m, difference between Sn and L or difference between Sm and L must be less than epsilon by using definition of limit of sequence. Okay. So now whenever we sub epsilon, we get a derivative epsilon by 2 also for our adjustment, because this is also very small number. So when n and m are greater or equal to m, both these inequalities are true. 1 and 2 are valid. Okay. So whenever n and m are greater or equal to m, these both inequalities are valid at the same time. Okay. So now you will take difference between Sm and Sn. Okay, whenever n and m greater equal m. Okay, so we will make some adjustment here. So this is equal to Sm minus L plus L minus Sm. What we do? What we have done? Just add L and we have subtracted L. So this and these are equal. So in mod we have subtracted L and added the L. Okay, so there is no change in the value. So we can write here bracket also. Now we know mod of a plus b, triangle law of addition. Mod of a plus b always is equal to mod a plus mod b. This is a, this is b. So mod of a plus b is less equal mod a, that is mod of Sm minus L plus mod of L minus Sm. And we are proving this for all n and m greater equal to m. So since n and m are greater equal to m, this mod Sm minus L is less than epsilon by 2. Also this mod, okay, so this Sm minus L mod of this is less than epsilon by 2. Similarly, mod of L minus Sm is equal to mod of Sm minus L, because mod of a minus b is equal to mod of b minus c. So mod of L minus Sm, that is mod of Sm minus L, is also less than epsilon by 2 for n greater equal m or m greater equal m. So whenever n greater equal n and m greater equal to this capital M, this difference or mod of Sm minus L is less than epsilon by 2. Also this difference mod of L minus Sn or mod of Sn minus L, mod of Sn minus L or mod of L minus Sn are same, is less than epsilon by 2. So this is also less than epsilon by 2. So this implies, and this addition is equal to epsilon. So this implies mod of Sm minus Sn is less than epsilon for all L and m greater equal to this capital M, that natural number m. So for any epsilon greater than 0, we have find m such that difference between Sm and Sn is less than epsilon for all n m greater equal to m. And this is the definition of Cauchy sequence. What is the definition? A sequence Sn is said to be Cauchy sequence if for any epsilon greater than 0, we can find m, a natural number, such that difference between Sn and Sn becomes less than epsilon for all the values of m and n greater equal to that m. So for any epsilon greater than 0, we have find m such that difference between Sm and Sn is less than epsilon for all m greater equal to this m. This implies the sequence Sn is Cauchy sequence. Okay, so this is the proof of every convergence sequence is always a Cauchy sequence. Okay.